For our second example that we're going to do is I'm going to try to work through this example so that we're able to pick apart the important points. Now, I think what are really important ideas is to pick out where our horizontal asymptotes are, where our vertical asymptotes are. I'm going to call these stationary points. And I suppose that's it. Now, here's my graph, y is equal to x squared. I'm going to graph this by transforming the graph below. Now, these are the main ideas here. So x, y on my first graph map into point x comma 1 over y. That is, I'm trying to graph the reciprocal of the function. So what are we able to see? Now, important idea number 1. The x-intercepts on f of x become the vertical asymptotes on y is equal to 1 over f of x. So why is that? Well, simply 1 over 0 is not defined. And let's just look at our denominator. Any constant divided by a number that gets exceptionally close to 0 will become very large. Idea number 2. The horizontal asymptote of y is equal to 1 over f of x is equal or is y is equal to 0. Now, I don't really like this too much. I think last year we took a lot more formal and thorough look, but it is what it is this year. Now, I'm going to move on to the next point, and I'm going to call this a stationary point. There are a couple of very important points. Now, I'm just going to say this is on y is equal to f of x, and obviously we move into y is equal to 1 over f of x, the reciprocal. So very simply, now here's a thought. I'm just thinking here. I wish that I knew of a value of x that I can think of so that when I take the reciprocal, it's the same. Can you identify the number y so that when we take the reciprocal, it is going to be identical? Yeah, I hope you got it. So if we have point, sorry, let me take that away. If we have point x1 on f of x, and we transform that, it stays the same. So wherever our y value is 1, we have a stationary point. You may want to write that down. Wherever our y value is 1, we have a stationary point. And I'm sure there's clever people in the crowd here, likely you, who said, well, how about wherever x was negative 1? Well, that is also true, is that if y was negative 1, you take the reciprocal, it becomes 1 divided by negative 1, which is negative 1. This is also a stationary point. Really, really important. I think that I have a lot of information, and let me just start graphing. So here's my function, y is equal to x squared. There's my parent function. Using idea number 1, there is my 0 of f of x. What do I know? I know that here, this will turn into a vertical asymptote. So I'm going to put a dotted line, by the way. Has to be dotted, otherwise you're losing marks. There's my vertical asymptote. Has to have arrows at the end because this line is continuous forever. There we have it. There we have it. There's my vertical asymptote. Now my horizontal asymptote will be y is equal to 0. So very similarly, oh, that one got a little bit high, but no worries. There's my horizontal asymptote. There's idea number 1 and idea number 2 expressed on a graph. Now a stationary point. I love stationary points. Why? I just go to the graph and ask myself, where is y equal to -1? Well, the graph is never equal to y is equal to -1, right? My parent function. But where is my parent function equal to 1? Or where is the y value equal to 1? It's equal to 1 at 2 points exactly. Right there and right there. Would you believe it that I actually have 2 points on my reciprocal function now? Now I just simply employ this idea and I'm off to the races, I think. Here I have 0.24. That maps into 2 1/4. Now I know that as my graph approaches -infinity, it gets closer and closer to this. So there, I've graphed this over there. Here, now this is another defined point, -2, 4. So -2, 4, now just to be explicit, maps into -2, 1/4. So -2, 1/4. There's another point on my graph. And as the higher the y value gets on my parent function, the closer the reciprocal gets to 0. You should probably discuss that point if you have questions about it. Now, I'm just going to take this value right here. A lot of you guys are asking, well, why that value? And I asked myself, why not that value? I have a good arc here. I'm wondering what this function looks like here. So when x is equal to, I don't know what this x value is, but the y value looks like it's about 1/2. So the x value stays the same, but that maps into 2. This is, I don't know the x value here, but the y value is 1/2. That would map into 2. Now I'm going to take another point, maybe switch it up. I'm going to switch up to blue, and I'm going to get even closer, right there. What is the y value there? I don't know, but it's less than 1/2. I'm going to call it 1/4. So what is the x value? Well, the x value is a little bit to the right of my previous observation, but now my y value is, I'm going to say, is 1/4. So this is going to go up here. So it's important that they have the same x value. There, same argument can be made. And I'm just going to simply connect my dots. There we have it. All right, so let's just talk about some brief ideas about numbers. And we're going to be revisiting earlier grades. If a number is positive, the number is negative. If the number is positive, what is the reciprocal? Well, the reciprocal of that number, I don't know. What are you thinking, Mr. Morin? I have no idea. Let me just make up a number, 7. If the number is positive, like 7, the reciprocal will be 1 over 7, which is also positive. If the number is negative, the reciprocal will also be negative. That is really important idea. Now, let me move on to other ideas. Now, I'm talking for some reason about numbers, not even about functions. It seems like I'm going back to grade 8. But this is really important. Now, this is a harder notion. If a number is small, okay, so if the number is small, the reciprocal, I don't know, what are you thinking of small, Mr. Moore? I don't know, maybe 1/10 small. When I say small, I mean less than 1, like here, where the y values are less than 1. So if the y value is small, the reciprocal is large, right? Because here's a small number, 1/10, the reciprocal is 10. Here's a very small number, 1,000th, the reciprocal is 1,000. So the smaller the number we have, the larger the reciprocal. That's going to be important in thinking about graphs. Now here, if a number is large, what am I talking about now? It's hard to keep up here. And it seems like it has no purpose, but if a number is large, what is large? I don't know, more than 1 generally. So 7. If the number is large, the reciprocal is going to be relatively small. And the larger the number, oh my God, that's a large number. That is 1 million. Look at how small our reciprocal is. Generally speaking, the larger the number, the smaller the reciprocal. But if you notice that no matter how large our number is, it will never be 0. The larger the number, the reciprocal approaches 0. So really we're talking about the y values. All right, I hope that I haven't confused you too much. But these brief ideas about numbers are going to be so incredibly important. Let's revisit the graph. If I noticed here, my graph was positive. The y values are positive. Since my y values are the ones being transformed, what do I notice about my reciprocal function? Well, my reciprocal function was positive. That is, all the y values were positive. Also, wherever my y value was small, when I took the reciprocal, it got large. And the smaller the y value on my parent function, the higher and higher this reciprocal function will be. Now, a horizontal asymptote over here and over here, we had fairly high or tall y values. So when we took the reciprocal, they got closer and closer to 0. I'm hoping that we're starting to put this together. If you have any questions, feel free to ask.